Roughly prompt. Okay, well, good afternoon and welcome to the EM course. It is winter. This is a picture right outside of NYSBC. The wind wasn't that bad. That was actually a snowblower blowing it, but it's great that we have a virtual meeting because we don't have to have a snow day and we can continue forward. So we have now progressed beyond our intro or EM fundamental section to the real flipped classroom. And I just want to remind people of the format because this is a slightly different format. And now forward, we have guest lecturers, and I'll get into that quite shortly. The idea is that you watch videos on the subject ahead of time, and that is to give you background knowledge. So the homework assignment was to watch the upcoming lecture. And then the class itself will be structured slightly differently moving forward. We'll have a brief introduction to the guest lecturer. Certain topics and certain fields are quite mature, but from when the pre-recorded lecture was posted, some new developments may have occurred. So we'll give some time to give everyone an update. And the bulk of the course should really feel more like a roundtable where we have engagement, where if you have questions on the subject matter, we can clarify that. And the purpose for this is to go beyond what a standard lecture would be. And if you just want to see a standard lecture, not only do we have a lot of pre-recorded ones from last year, but the previous years, and we also have a whole host of information coming out now from the national centers with a lot of curriculum development. So what are we doing today? Well, today we're starting off on our EM crystallography section. There'll be two lectures in this section, one on MicroED and 2D crystallography, and then the last one on helical reconstructions. Our guest lecturer today is Bill Rice, coming from NYU. He's coming from NYU Langone Health and also is the core director from the Cryo-EM facility there. And so we want to welcome Bill. The first thing that we're going to do to just give people a lot of time to get settled is we're going to introduce Bill to you and sort of ask him a little bit more of his background so you can get familiar with him. And then we'll segue more proper into the class itself. So I'll stop screen sharing so we can have a better view of everyone. So welcome, Bill. How are you doing today?
Oh, good. Snowy, yes. But I'm warm at least in here.
Okay. So EM has progressed quite a bit. So how did you first decide to get into the field of cryo-EM out of all the scientific subjects?
Yeah, so in my PhD work, I was doing kind of studies on the calcium ATPase and doing a lot of site-directed mutagenesis and to get at the structure function relationships in it. But I really wanted to get into structure. And at the time, it was almost impossible to crystallize membrane proteins, but it was possible, or rather to get in 3D, but there were 2D and helical crystals of them. And so I got into it by basically talking to David Stokes at some meetings, and he had been doing 2D crystals of that. And so I moved into doing, actually, I was studying, instead of, for my postdoc work, I started studying the sodium potassium ATPase, which is related. And very quickly, I was lucky to get 2D helical crystals of that, which is, so I basically started off in EM doing helical crystals of a membrane protein and cryo-EM of that.
Okay. So we have been talking about microscopes quite a bit here, and there has been a push for making microscopes easier, including automation. But everyone has their own favorite microscope. It might have been the first microscope they used or a more recent one. Do you have a particular microscope that you love to use?
Right now, I would say probably here we have a Krios and an Arctica, and probably Arctica just because it's a little bit simpler and a little bit easier and easy to get going on. Krios is also an excellent microscope. I really like that one too, but it's just because of the energy filter, mainly you have a few more things to worry about. The first microscope I used was a CM200, which was a Philips CM200, which was before FEI bought the microscope thing from Philips. So those ones were, that was before we didn't have CCDs, so we had to take everything on film. You could only take 50 films before you change the film. And doing all the focusing was a lot hard. Everything was harder. You had to focus on a phosphor screen, like in real space. by just sort of minimizing the contrast and do the astigmatism by making the grains of it look as round as you could. And it was just a lot harder.
I remember that. So overall, that brings up a good question. How do you feel the cryo-EM field has progressed over the years from, I guess, your early CM days to now the more autoloader systems?
Yeah, well, now it's like a lot easier and more robust, and I don't know, just it's easier to get going, and has brought a lot of more people into the field. And of course, since the resolution revolution, when the new detectors came out, it's sort of really expanded the field. So it's been quite exciting to see kind of a real revolution happen in what you've been working on. So that was quite amazing. I mean, everyone hoped that the pictures would get better, but I don't think, it turns out, the microscopes were always really good. It's just that the detectors weren't. And so just improving the detectors really made a difference. Of course, the new ones my scopes are more stable, and automation is much better, and everything else, but it's just kind of amazing.
Are there any fields that are using EM now that have surprised you? Any fields beyond the classical structural biology fields?
Yeah, I would say, I mean, probably related to MicroED, just looking at getting structure of small molecules by X-ray diffraction, or by EM diffraction of, using microcrystals or nanocrystals of small molecules. I never thought chemists would kind of get into it that way.
Mm-hmm. And before we get into the topic of MicroED and 2D crystallography proper, I guess the last question I'll ask you, what do you feel are the new frontiers and challenges, or even opportunities in our field?
Yeah, I think, single particles come a long way, and now it's almost routine to set up once you have a good sample, once you have your protein and biochemistry worked out. But I think that certainly the next thing is, more looking at your proteins in the cell, and doing tomography of the cell, or milling part of a cell and looking at part of a cell to see what the protein looks like in its native environment. And then I think there the challenge is basically identifying the protein, because it's like in a whole soup of everything else, and figuring out what is what in there is a real challenge, I think. So I think, but that's also a big opportunity. I think seeing things in their native context is really going to be the next step.
Okay, wonderful. I think now is a good opportunity to give you a chance to show how MicroED and 2D crystallography has really progressed. From when you gave us the lecture last year, I think there's been a huge explosion of not just instrumentation, but different fields getting into MicroED more so than before, because it's moved beyond proof of concept, and a lot of small molecule people and protein practitioners are making good use of it.
Okay, yeah, thanks. Oh, I think, is my screen still shared?
No, you'll have to reshare.
Let me just...
When I put the slides up, I stole the screen.
Oh yeah, I see. I guess, yeah, so I prepared a few slides of, I realized I sort of cheated in my talk, because I didn't really talk about 2D at all, and just talked about MicroED. So I'll just go through a little bit of what 2D crystallography is and sort of what the difference is, because there were some questions about that. So with 3D crystallography, you have basically you're making a 3D lattice of your protein. So you have information in all 3 dimensions. 2D with crystallography, which came earlier, was mostly used for membrane proteins, because they're sort of naturally limited to one plane, being, sitting in the membrane. And so sometimes you could arrange things so they were organize themselves into a 2D lattice through this in the membrane. And let's see, let me start the slideshow. So can you see my mouse? I think I can change the mouse on. I'm not using my normal computer, so I'm just, anyway, can you see the mouse at all or not?
I can see the pointer.
Okay, yeah. So to do 2D crystallography, say of a membrane protein, you basically would express your membrane protein of interest, and then purify it by solubilizing it, and then mix it in with other lipids, maybe native lipids and maybe other lipids you'd have to figure out to screen, and then dialyze out the detergent. You could also remove it with other things like BioBees, but most commonly dialysation was used, so that you would hope when when the detergent diffused out, the protein would go into the lipid bilayer and form some sort of ordered array and form 2D crystals. And then you'd have to screen it, which was usually done by negative stain EM, and then freeze it and go into 2D image collection, which we'll get into to eventually get a 3D structure. But it was really, really a lot of work, and still would be. And there's number one, you have a lot of parameters to worry about. So besides the normal parameters that you worry about for regular crystallography of proteins, you have to also have to worry about what type of lipid you're going to try. So there's a whole bunch of lipids you can try. There's a whole bunch of detergents you can try as well. When you solubilize your proteins, you have to figure out what detergents it like. And then also what lipid to protein ratio to add. So what the mix should be so that it goes into the membrane such that it's packed together to form crystals, but not too packed together or not so loosely packed that it doesn't form crystals. So there's just becomes a large matrix of things to screen. And you couldn't really screen it in the normal way, like where you do for 3D or even possibly MicroED, where you look at the crystals by light microscopy. What you had to do is pretty much do negative stain EM of them. So for every condition, you'd have to make a grid, do negative stain of it, and then look at it under the negative stain, and hopefully you'd find something like this where you actually see crystals. But it's very, very laborious. So there were some works where they, and actually one was at NYSBC, where they set up automated 2D crystal screening of it, but even still, it was a very slow process. And then once you froze the crystals, it was also a different method. So it wasn't just simply, getting a quantifoil or C-flat grid and adding your sample and plunge freezing it. What you needed was you need a flat, since it's a 2D crystal, you want the crystal to lie flat on a carbon layer. So you'd have to have make your own carbon, which is nice and thin, kind of put it onto a grid. Usually you'd have the carbon film in water, you put the grid in and kind of lift it up so that the carbon film lies on the grid. And then add some trehalose to it to sort of as a cryoprotectant, basically, so it would not, because you're not going to plunge freeze it in ethane, or you're going to just sort of freeze it more slowly. You add your protein to that on top of the grid, and then let it air dry for a bit, blot it and let it air dry, and then hopefully the protein crystals settle down on the carbon, and then you freeze that put that in the holder and freeze it and put it in the microscope, and then image it cold. But it was sort of a different sort of process. You also got, because of the trehalose amount of, it's basically a type of sugar, it would lower the contrast quite a bit. So the lattice itself might even be invisible to see until you did an FFT of it. And there's another method where you could do a carbon sandwich and kind of put carbon on both sides to kind of hopefully make it flatter. But it's quite a, it's a different sort of, it was a sort of a different technique to freeze. Of course, it kind of came up a little, I think, a bit before, Dubuchet came with the plunge freezing method too, or maybe we were around the same time, but it was sort of early days. And plus, even though you do that, the crystals still were not perfectly flat. So the flatness could be caused because of the carbon support film might not be that flat, and then the carbon freezes at a different, when it freezes, it has a different thermal expansion coefficient than the copper that was more commonly used. So it causes the carbon film to kind of wrinkle a little bit, which makes the crystals not flat. So molybdenum grids were often used, and because they have a much more similar thermal expansion coefficient compared to carbon, as with carbon, so they would stay flat when you freeze them. And then you could also be more careful when you evaporate the carbon support films by not sparking it. I don't know if you ever evaporated carbon. Usually you have it sparking a little bit when it evaporates, and it evaporates very quickly. But if you kind of keep it below the sparking temperature, it will be a higher quality carbon. So 2D crystals is basically, it's just like you have a fundamental unit in 2D. In this case, there's this star, and they may associate with itself by flipping. There might be one next to it that's flipped, so you'd have a protein that's pointing up and a protein that's pointing down, and then you sort of get repeating units of that, and that's basically what forms a crystal. And there are various symmetries within the crystal, so or which is similar to the number one, you could have symmetry within the protein itself, like you could have two-fold symmetries like this S, so you could rotate this 180 degrees and it would looks the same, or a threefold symmetry or fourfold symmetry or sixfold symmetry. And so these are all you can get these different symmetric lattices of within the crystal which have these different symmetries. And within the crystal there can be different types of symmetry. There can be some sort of a mirror symmetry or a glide reflection, which is basically you move it a little bit and then mirror it after that. And there are, for 3D crystals, there are 65, I think, crystallographic space groups which can be found. And for 2D crystals, there are only 17 plane groups. So it's a bit fewer. This is sort of a quick drawing of them. The P1 is, of course, is no symmetry at all. P2 is twofold, and so on. But you can have and of course it's unpredictable what crystal symmetry you will get. But you take advantage of the fact that it's symmetrical, and you basically do everything. Basically, all of the work is sort of done in Fourier space, because from your Fourier space lecture, you know that it sort of becomes a lot easier to deal with repeating things in Fourier space. So, for example, say you have an original image, and which you don't really even see any contrast in this image, but if you calculate the Fourier transform of it, you see these spots, which would be a really good sign. That means there's something repeating very strongly. And as a first sort of step, you could filter these spots by, say, just including the spot themselves and kind of filtering out all of the other background. So that you're just looking at the Fourier components of the diffraction spots, and then do an inverse transform, and then suddenly you would see contrast, and you would see what the underlying lattice is, and some what the 2D repeating unit is, and you'd see some details. With 2D crystallography, you're mostly collecting images, and then calculating power spectrum or Fourier transforms. And when you do the Fourier transform of an image, it has each of the spots has an amplitude and a phase. And the amplitude is basically the brightness of the spot. Now, it turns out that, because you're doing images, you then are affected by the CTF, so the contrast transfer function of the microscope. So there are nodes of the CTF nodes within the image where there's no information transferred, and the brightness of the spot is going to vary as it's multiplied by the CTF. So because of that, even though you have amplitudes and phases, the phases are all right, but the amplitudes are not that accurate. So in order to get a better estimate of the amplitudes, you could take a diffraction picture of the same type of crystal and get the amplitudes from that. Now, when you take a diffraction image, you lose all of the phase information, but you do at least get accurate amplitude. So that helps a little bit. So in this hybrid picture on the right-hand side is a diffraction image of a crystal, of a 2D crystal, where you can see the diffraction spots going out to pretty high resolution. And on the left-hand side is the Fourier transform of a similar crystal. It's not the same one, probably it's a different one, but has the same spacing. And you can see that the spots are quite a bit weaker, and you may or may not be able to see it's a bit modulated by the tone rings. I think this is a 0 of the tone ring here and another one here. But you basically you sort of have to collect both sorts of information for 2D crystallography, images and diffraction patterns. And of course the diffraction patterns are easy to collect, actually, because on any microscope, even 20 or 30 years ago, it's the same thing. You basically just change the lenses such that instead of magnifying the image onto a screen, you change the lens strengths and you magnify the diffraction pattern onto a screen or onto your detector. So you just press a button and microscope reconfigures itself. So that's not hard to do. But you did tend to collect both types. more images than you didn't need to collect too many diffraction patterns, but you needed some just to get accurate estimate of the amplitudes. The processing was complicated, I would say. I mean, this is, you had to do, you had to sort of, the main thing is you had to unbend them. So sort of one of the crystals themselves, even as flat as they were, they're not perfect. So there may be some distortions in it. So basically there are programs where you sort of box out a reference region of it and use that to sort of do a cross correlation map of the reference region across the entire image. And it would sort of use that to do a profile of it and you would then figure out how much things have bent or how much things have moved within the crystal where they shouldn't move, and make a sort of unbent image where you've sort of removed all of these distortions. And there used to be a whole bunch of, these all were individual programs that you would have to run individually to sort of do all of this. Eventually there was a nice 2DX graphical program by, I think, Holger Stark's lab that made a GUI into it, which made it a lot easier, but still it was kind of a more difficult, I would say, than single particle. You also had you would take many pictures of crystals, and so you had to merge them. So you had to sort of basically find the same phase origin of them so that everything is lining up, so that you could then have the power of averaging many different images, and then you would get a really high quality image which has good amplitudes and phases in its FFT. And then from that, you would get a projection map. Because the crystal is only in 2D, and so far I've only been dealing with one image or an image of untilted crystals, you only have information that's been sort of amplified. The sort of high resolution information is only extending in 2D. You don't have any real 3D information of it because the crystal is only a 2D crystal when you're looking at it in one view. If you wanted to go to 3D, you have to then take many pictures of the tilter of these crystals in a tilted orientation, and that basically comes from the projection theorem, where you're taking a projection image of a 3D object is the same as a central slice through the 3D transform of that 3D object. And so if you take many tilted images and line them up the right way, you can then get a 3D reconstruction of it because you filled in a whole bunch of central slices of its 3D Fourier transform. This is very similar to tomography, but it has the same problem, is that you can only tilt to about 60 degrees, plus or minus 60 degrees. So there's always a missing cone of a cone of missing information in a 3D Fourier space where there's no information because you can't tilt that high. And of course, the crystals also are naturally, they're all oriented the same way. So there's no way you could really fill in that missing cone by taking more pictures because they're all in the same orientation. But even doing that is kind of difficult because you have to, if you look at the 3D transform of this sort of 2D lattice, a 3D transform of a 3D lattice will be a 3D lattice in inverse space, but in a 3D transform of a 2D lattice will be, you'll sort of have a 2D lattice in two directions, say the A star, B star direction, and then just straight lines going up in 3D. And so when you tilt your crystal in Fourier space, you're getting basically a central section through this, and you'll measure the amplitudes and phases of it as of the same spot with different tilts, and then that will end up giving you information in 3D. And so they would plot these so-called the lattice lines, which are these sort of amplitudes and phases along these lines. So each of these is a certain point, a certain diffraction spot, and then you tilt it between 0 and 60 degrees, and then you could plot the amplitude and phases as you tilt that lattice line, and then that would give you the 3D information. But merging all that was also difficult because you can't suddenly tilt too high. You have to sort of work your way up from 0 degrees because you have to still figure out what is what and what how to line things up in order to merge all of the data. But So basically, in a nutshell, the 2D crystallography is kind of one of the more difficult techniques. I would say you have to take a whole bunch of images of your crystal, determine its lattice parameters, which is in unit cell dimensions, unbend it, correct for the CTF, figure out again the symmetry of it, and then collect, merge a whole bunch of data, and then also merge in tilted images data to get a 3D map. So in a nutshell, the pros and cons of 2D electron crystallography of membrane proteins versus, I guess, other techniques. The number one pro I think that's still true is they're studied in their natural lipid environment. They're not solubilized anymore. They are still in a lipid bilayer, so there should be no worry that there's anything distorted that way. But I think it has a lot of cons. So the screening of 2D crystals is slow. It may take up to weeks for the crystals to form by this sort of slow diffusion. I would call it's pretty tedious, takes a lot of time to screen. The data collection also is difficult because you have to collect many crystals and tilt them. The 3D map still will suffer from an anisotropic resolution because you have this is missing cone, and I would say that, and the software is certainly less well developed and a bit more difficult in general than for single particle analysis and tomography. But then so lately, I think when people now talk about crystallography, it's going mostly MicroED and not 2D crystallography so much anymore. So I just did another check. So electron crystallography now, there are now 149 maps. So there are quite a few. I would say I think almost double the number of 3D MicroED maps deposited since the last lecture. So it is growing. It is still a small portion of all of the maps that have been deposited, but it is becoming more of a it's becoming more popular. There's more. A lot of it was Tamir Gonen's lab, but there are more labs doing it now. Just as a sort of comparison of different methods, say, a number of, say, unit cells that you're working with when you're doing this averaging. So with single particle reconstruction, you're usually the final maps that people deposit have on the order of 10 to the 5 to 10 to the 6 particles, I would say. For 2D crystals, actually even 10 to the 4 to 10 to the 6 when I think about it. For 2D crystals, say you have a unit cell of about 100 angstroms by 100 angstroms, and your imaging area is 400 by 600 nanometers. That's around 1 angstrom per pixel on a K3. So then you're going to have around 2,400 unit cells per image. So you could think of it as, in a way, if you think of it in the single particle way, it's like all the 2,400 single particles all packed together. But the thing is, there's a lot less processing that you need to do once it's in a crystal because they're all ordered. They're all in the same orientation, ideally. So you don't have to, it's not like a single particle where with single particle, you're sort of doing crystallization in silico. You're aligning everything. The computer's aligning everything. Here, the thermodynamics are aligning everything. So then your calculation is a lot less because you have a lot more sort of pre-aligned stuff to work with. If you move up to 3D microcrystals, say your imaging volume you might have a 1 micron by 1 micron crystal, and it should be thin. So say it's 400 nanometers thick. That would give, with the same 100 angstrom unit cell, I think that gives about 400,000 unit cells per crystal. Now, if you have a small crystal, 3D crystal, which is big enough for X-ray crystallography, I'm not an X-ray crystallographer, but I think 5 micron by 5 micron by 5 micron is probably reasonable for a small crystal. So that would give around 10 to the 8 unit cells for one thing. So that's you're sort of, and again, everything has been oriented in the same way. So there's no alignment that needs to be done. So that's why your sort of thermodynamics or have sort of entropically given you a lot of information sort of naturally. So you have to do a lot less processing. In terms of computing power for a single particle, you generally need a cluster or a GPU cluster, or something with at least 4 good GPUs and a lot of memory, and a lot of disk space. MicroED can actually be done on a laptop. I went to the MicroED course in the first one, actually, in 2015, I think it was. And we basically, you brought a laptop and they gave us a Linux boot disk, which had all of the software on it. And you could do all of the processing just on the laptop. So you don't really need too much processing power. So if you have a computing setup which you were planning to do single particle or tomography on, that's more than enough than what you need to do the calculations for MicroED. They're very similar to the X-ray crystallography calculations, which so because it's sort of the same technique that's been done for so many years, the power of computing has increased so much that a standard workstation is enough. And by standard, I don't mean like a $20,000 one, but probably a $5,000 one is more than enough to do all of this stuff and have graphics too. So why would you use MicroED, say, versus single particle? I would say if it forms ordered crystals easily, if you can easily get crystals, you should probably use X-ray crystallography or MicroED. If not, and it's going to be a lot of work, I would say if it's, the limit seems to be currently around 60 kD. There may be something less than 60 or for single particle reconstruction. I know we've recently had someone got a 60-something 3.3 angstrom map of a 60-something kilodalton protein on the Arctica, so it's quite possible. It may take quite a bit of work, but I'd say if you can get crystals, it's faster, and either X-ray or MicroED could be faster. But if otherwise, single particle can be fast as long as things are well behaved. If you have small molecules like less than 60 kD, if it's a 30 kD thing, you're going to have to do some sort of crystallography because it's too small for a single particle. Or small molecules, drug molecules or things like that. Then if you can get them crystallized, then MicroED or X-ray is good. I think the advantage of MicroED is apparently a lot of molecules that when you just sort of dry them, they'll sort of naturally form these tiny crystals, and so you could just use them directly if you have it, if you know how to do it, and not have to try to go through the trouble of growing large crystals. And then say versus X-ray crystallography, basically it's a very similar experiment once you've collected the data. You have to worry about the wavelength of the electrons, which basically depends on the voltage, whether it's 200 or 300 keV. And you have to use electron scattering factors, but that's built into, I think, a lot of the X-ray software now. So I know programs like Dials and MOSFilm work for processing the data. I think most of the packages, at least those packages, I think probably a lot of the packages that they've now built them in because it's become enough of a popular technique that you can do it. I would say if you have large crystals and they're large enough for X-ray diffraction and they diffract well, you might as well collect by X-ray because there'd be no reason not to. If you're getting 2 angstrom diffraction or 3 angstrom diffraction or something like that. If you have tiny crystals that are too small, or if you have large crystals that don't diffract well, but you can perhaps look for small ordered regions. Well, there's a lot of mosaicities, so they won't be good for 3D of the whole thing, but you could use break off a little piece of it, then definitely MicroED would be good. But these are all complementary techniques, so I don't think the MicroED is not trying to replace X-ray crystallography. It's just something in addition to a technique in addition to X-ray crystallography and in addition to single particle or analysis of proteins to get structure. So it's just another way of doing it, basically. There was a question about what type of microscope. So most of the early MicroED work was done on a Techni F20, which is a 200 kilovolt FEG microscope. This actually came up. I went to Tamir recently gave a MicroED seminar in late December, which I went to, his teaching course. It was all online and it was like oversubscribed. So hopefully some of you went to that if you're interested in it. But I mean, I agree with he said, and I would totally agree, is that it's better to do it on a modern microscope just because of the stability of the microscope and the quality of the goniometer. For the MicroED to work, you need to be able to continuously tilt between plus and minus 60 degrees, say, without adjusting the stage at all. So you have to, without, so the field of view has to be constant. So you need a microscope that's capable of that. And if you don't have that, like an older microscope may have more trouble with the goniometer. Certainly if you can use something with a, with an autoloaders type system, which is a high quality goniometer and everything's much more stable. You don't have to worry about a side entry holder. It's just going to be a lot easier. You also need a camera capable of continuous collection. I have a slide on that next. Thermo Fisher has now commercialized this. They sell a MicroED package, which I think comes with the software and a C to D camera. And the MicroED package basically does most of the setup for you, and it's for Krios, Glacios, or Arctica microscopes. And so that can be one way to go. And then you don't really have to then do very much because basically the engineers will calibrate everything for you and make sure it's all working. And then it becomes more like a plug and go package. You still have to make the crystals, of course, and screen for them, but you don't have to worry about setting everything up and getting everything working. So that would be one way to go, especially if you're not an expert in diffraction or even an expert in just regular TEM, and you just want to get up and going. So that would be they've made that as one way. I don't know if JEOL has done that or not, but I imagine if the market becomes big enough, they would do the same thing. I'd say that the older or more low end the microscope, the more knowledge you'll need to bring, because you'll have to do more calibrations. You'll have to get it working. You'll have to just make sure it's all working. So I would say, the easiest thing would be a modern sort of mid-level to high-level microscope. So Glacios or Arctica, or even Krios would be good. Those are the ones I would have experience with. You probably would want to use a FEG, have a FEG microscope, a field emission gun versus a Lab 6 or a tungsten, just to have, that way the beam and everything is brighter and more coherent. It probably just makes the experiment a lot easier, especially if you get to high resolution. And I think just about all of them, there might have been one paper where they used a Lab 6. I think there was one paper that I had in my lecture where they used a Lab 6, but almost everything is done on a field emission gun at 200 or 300 kilovolts. But you don't need, phase plates. I wouldn't do anything, or energy filter. Energy filter presumably would help, but it's not necessary. The detector is important, so it needs to be a fast detector because you need to do this live imaging. You need to collect live movies while it's tilting. I think the first experiments he did were on a TVIPS F416, which is a CMOS detector, which has a live movie mode, and that works well still. The CETA camera will work, but it's not really optimized for it. FEI now makes a CETA D, which is a sort of a CETA which has a thicker scintillator, and it might have a slightly more advanced movie mode where it's easier to do collect movies. There was a paper recently, I think it was, again, the Gonin lab, they collected also on a Falcon 3. They sort of compared Falcon 3, a CETA D, and a CETA. And that Falcon 3 worked very well. But the Falcon 3 is a direct detector, so it's expensive and, easily damaged because there's no scintillator layer which sort of also helps shield the camera. So there'd be the potential of burning the camera if your beam stop is misaligned and the direct diffraction beam hits the detector itself. So that could potentially burn it. So that would be, and also you'd have to have Thermo Fisher disable the beam protection software. So because right now, as normally configured, you can't take diffraction images on the Falcon camera. The software won't let you, but that can be disabled. But those ones would be possible. I think the direct electron DE 16 or 20 would also work. I know at NYSBC they've experimented with using it. I think they had to make I think they said, I think Angie had said you'd have to make a modification to let it record images a bit longer, but I mean, that one also would work with the same caveat as the Falcon 3. It would be in danger of getting burnt by the beam. So I would say I wouldn't want to use a direct detector until I had a lot of practice doing MicroED using a regular, non-direct detector with a scintillation layer, because these ones, they're sensitive, but if you hit them with a diffraction beam, a couple of times, it's probably not going to hurt it permanently. It might take a little while for it to come back, but these ones you could definitely damage. There's a question about lipidic cubic phase crystals. And so there was a paper just this past October where they actually looked at lipidic cubic phase crystals. So it was more of a proof of concept paper, but the reference is here. What they had to do, they first thought they could just, the problem with lipidic cubic phase is it's very viscous, so you can't just put a blob of it on a grid and blot it off with filter paper to get it thin enough to freeze. It's because it's just too viscous. So what they did was they tried adding additives. So they either added things like MPD, which sort of converts it to a less viscous sponge phase, sort of, I guess it just sort of changes the matrix of it so that it's slightly less viscous without damaging things. Or they treated it with a lipase, which to sort of break up some of the lipids and convert it to what they call a two-phase liquid system. So it seemed to, again, it's a sort of a proof of concept paper where they grew proteinase K crystals in this lipidic cubic phase and then treated it this way and saw that they could still get 2 angstrom maps of it. And they also showed that they could get a projection map of cholesterol, I think just sort of showing that when they did a real protein, this adenosine 2A receptor, they only got diffraction to 4.4 angstroms, and they really only calculated a unit cell of it. They didn't really do any map of it. But I suppose I imagine the reviewers wanted them to prove that it was what they were looking at was this and not just cholesterol. So then they did a crystal where they added extra cholesterol to this lipidic cubic phase and could see cholesterol diffraction. And they were all, because they only had a severely preferred orientation for some reason, so they could only get a projection map of that. But it did seem to, this seems to be the way. Basically, you have to just somehow make it less viscous so that you can get it onto a grid. That's the main challenge. But it could be something good for MicroED. But it looks like it's a proof of concept, but it's could work. So then I just copied a bunch of questions I got in the email, and I'll sort of go through them one by one, I guess. So how long does a MicroED experiment take? So 2D crystallography is a long time. MicroED is less. So you can, I would say, you can screen through it. Screening through a grid for crystals would be sort of like screening for a single particle. You're looking for whether you have crystals or not. So it could take a long time or not, depending on how sparse the crystals are or how rare they are. And then once you find a crystal, you can very quickly take a diffraction image of that crystal and see if it has a diffraction pattern and if that diffraction pattern goes to high resolution. So that could be reasonably fast to screen through. So, how many samples in a day, it's hard to say. I mean, you might be able to get through a dozen grids in a day if you look at it and don't really collect too much, or more, depending on how fast you go through, how easy the crystals are to find. So it sort of depends, but you would have to do, look, at least do an atlas of the grid or something like that to have an idea whether you see crystals or not. And then you would do diffraction patterns of a few of them just to sort of see if they're diffracting. How many samples can you get on a grid in practice? And I think, even though I said you could do more than one, probably most people are doing one sample on a grid, but you can, if you have an auto loader system, you can load 11 or 12 grids at once. So that would probably be the way to go, would be 11 or 12 grids of different samples. And then you would probably, right now, one sample per grid would probably be the easiest thing. I think when they put more than one, it's sort of, again, more of a proof of concept. And then, how would you know what sample you're imaging? I guess you'd have to solve the, if you could figure out the lattice spacing of it, that might help you a lot. But hopefully you aren't looking at so many that you can't sort it out. I already went through it sort of microscope. I haven't really seen anyone do 100 keV, but 200 keV has been common, or 300. So I sort of went through crystallographies. MicroED only working with small molecules. So so with proteins, with MicroED, you still have the phase problem that X-ray crystallographers have. So you have to figure out the phases because you're only collecting diffraction patterns. So for proteins right now, there's nothing analogous like an X-ray to MAD or SAD phasing where you can figure out the phases that way, or heavy atom replacement. So the only way is molecular replacement. So, however, I think recently Google had this great breakthrough for this AlphaFold where they could sort of calculate the 3D structure of small proteins using from de novo. And so potentially, if that really works, it may not be perfect, but it might give you something good enough if it's a small enough protein that AlphaFold works for it. Perhaps you could use that to get an initial model if you don't have any sort of molecular replacement. But for smaller molecules like peptides, you have to have the way to do that is direct phasing. Actually, is you as long as you have diffraction that's better than 1 angstrom or so, and the protein itself and the molecule itself is relatively small, you can do direct phasing methods and solve the phases de novo. For proteins, they're too big, but for peptides and small molecules, they're not too big, and basically the high resolution structures that have been solved of them have been done de novo. And so how easy is it? I think it depends on the quality of the data. So as long as it's diffracting well, it's easy. If it's not diffracting well, it's not easy. So the next question is, I sort of answered about lipidic cubic phase. So basically it's just, I'd say work in progress. Fib crystals is a lot of effort. Yeah, it seems to me that fib crystals sound like quite a lot of effort. Beyond proof of concept, if I'm an X-ray crystallographer, a lot of microcrystals, this is prefer to go. I would say, so fib crystals so that means the thinning of larger crystals by fib milling to make them small enough for MicroED. I have a feeling that, if they're that large, it's probably, hopefully you could go for X-ray crystallography. I don't think fib milling of it is likely the way to go unless nothing else works, because it is much more work, and you need another microscope, and it sort of complicates things. So what type of programs and computers? So for the program, basically you need the sort of standard X-ray crystallography programs like Dials and MOSFilm will do the processing, and I think a lot of them have built in the scattering factors for X-ray. And for a computer, you don't need very much. I don't have any benchmarks, but if you have a computer that will do single particle, you're fine for MicroED. Let's see, sort of answered number 1, I think. Is it because of crystallization diffraction ground that we're able to look at molecules that are much? Yeah, so the reason you can do, the reason crystallization or MicroED, all this crystallography works for small molecules while they don't work for single particle, is because if things are too small, you can't see them by single particle. So less than about, say, 50 kD is currently almost invisible by single particle. So you can't pick the particles because you can't see them, and so then you can't align them, and so none of single particle works. When they're in a crystal, they're sort of, because they're all ordered, when you do a Fourier transform or collect a diffraction pattern of it, all of that information is adding up, and so you're getting the information from many molecules at once, and so you're sort of using the power of averaging large numbers of molecules. So that's why it works for for things that are small. It obviously works for big things that are large, but if you can do, if it can also be harder to get crystals of things that are large. Crystals need to be frozen using MicroED. I would say protein crystals need to be frozen, or peptides or things that are naturally hydrated need to be frozen, because they're in water, and you can't just if you put liquid water in the vacuum of the microscope, it'll immediately evaporate in the vacuum and probably crash the vacuum of the microscope, because it's volatile in the vacuum. So anything that has water in it needs to be frozen, and kept it close to -180, at least below about -150, so that it doesn't sublime in the vacuum of the microscope. So that's why crystals of proteins or things that are naturally hydrated need to be frozen. For small molecules, if you can get powders of them, they don't need to be frozen. You could collect MicroED of them at room temperature, although they would probably be a little bit more sensitive to the beam, so you might get them damaged faster. If you're using an autoloader system, then the autoloader system is naturally cooled. So, you need to, because it's naturally cooled, you don't have to worry about it. But so I would say powders don't need to be frozen, but things that are hydrated need to be frozen. Do I see a situation where MicroED surpasses Cryo-EM popularity because it's, I don't know if MicroED will be as popular as Cryo-EM. I have a feeling Cryo-EM has become very popular because it's the single particles. I guess you mean single particle Cryo-EM. So the single particle Cryo-EM is popular really because it works very well. With MicroED, you then have the sort of what I'll call the pain of getting crystals again. So I don't think it's going to be as popular. I think it could be popular in some things where crystals of small molecules are easy to get or easier to get. But I don't think it's, it's hard to predict the future, but I think probably more and more people are going to be wanting to look at bigger things and looking at kind of molecules in context. So although I think MicroED will keep growing in popularity the easier it gets to do. Let's see. Is it beneficial to look at single particle cryo images diffraction mode? Yeah, so single particle in diffraction mode isn't very beneficial because there's no order. So you'll be looking at the average of everything, but it won't sort of make any sense. Because things are not ordered, there's no information that's adding up as discrete diffraction spots. So it doesn't really help you at all to sort of average everything in the field of view, apart from maybe seeing if there's ice crystals or something like that. Why is this method not at least surpassed X-ray crystallography? I think X-ray crystallography is a lot easier. It's a lot more well developed over the past 3 decades or so, or 4 decades even. Since it's become more of a popular technique. Synchrotrons have a lot of time available. It's not hard to get time on a synchrotron if you have crystals, and there are a lot of people to help you. And with MicroED, it's currently more of a niche. It's going to probably keep growing, but I don't know if it would surpass X-ray crystallography, because that has worked really well, and there's a large number of people who are doing it. This is better suited for nanomaterials. So I think the MicroED is suited, I think, for smaller molecules. So say small proteins that are less than 50 kD and small molecules, peptides, things like that, where you can do ab initio phasing. So I think it's suited for basically for things where you can get tiny crystals. I mentioned number 8. So he mentioned the collecting of the images in diffraction mode would probably fry the detector. So basically, the thing is, whenever you collect a diffraction pattern, you always have a beam stop that stops a direct beam. because you have a very, very bright direct beam that's not diffracted and that goes straight through. And if that beam hits the camera, it's bright enough to damage the camera. So what I meant was if the beam, it's very easy to have the beam stop misaligned for a second or make a mistake. And then as soon as you make that one mistake, you could ruin the camera. The Falcon 3 is a direct detector, so it's not protected by a scintillating layer. So the electrons are hitting it directly. So it is quite susceptible to damage by an intense beam. And then I'll one more, and then I'll just get to the chat. So do I have any general comments or suggestions regarding pre-screening? Yeah, I saw that the same paper where they used basically fluorescence to sort of, or nonlinear optics to sort of screen for crystals. I haven't used it practically, but they do talk about this. I sort of saw the review of it. I think it's whatever I think I would say, anything you can do to avoid having to screen raw things in the microscope is better, because screening in the microscope is always very slow because you have to sort of do one grid at a time. So if you can screen by looking at it through optical microscopy, using either fluorescence or something, that would be good. And let's see, I can go to the chat questions now. So the first chat question is, to form the microcrystals, do you need as much sample as when you make crystals for crystallography? I think so, yeah, because you need to have enough. Even if the protein crystals are small, there needs to be a high enough concentration that you're forcing the protein to crystallize out of solution. So you do need as much sample in terms of concentration as when you make proteins for crystallography. Now, you're only going to be using a tiny little bit of it to put on a grid, 2 or 3 microliters. So it's possible you could make the drops smaller or something like that, or the robot. You could use I guess you could perhaps use the more pure screening robots where they make really, really tiny drops, and then take advantage of the fact that you don't need a big volume. But I think you do need the same high concentration because you need to crystallize the protein. Are most crystallization buffers used in X-ray work compatible with MicroED? I think so, yeah, I would say, because you're sort of, normally for single particle, you don't want to have all of these things like PEG and, these, carbon containing things like glycerol and things like that to sort of, that make that are used as cryoprotectants or as used as crystallization things, because they would lower the contrast. But because you're looking for crystals, and the crystals are these sort of big solid objects, you're not as hurt by that. So I think most of the crystallization buffers are compatible with MicroED. Yeah. As long as you can still, you might have to blot it a long time to get the ice thin enough that it's still electron transparent. That is one thing, is that you still need to have, the ice still has to be thin enough that the electrons get through it. Along the same line, what kind of solvent background is best for MicroED? Yeah, I think, because you're collecting diffraction patterns, you're not as hurt by the solvent background, because you're not imaging, you're not looking for this small molecule that's floating in solution. You have a crystal that's easy to find, and you do a diffraction pattern of it, and you're only looking at the diffraction spots. So that I think that helps you a lot. Now, again, the ice that it's frozen in has to be thin enough that the beam gets through it. I suppose you might, in this case, if the ice is kind of thick because you can't get it thin for some reason, you could be helped by having an energy filter, because that would help get rid of the inelastically scattered electrons in the that might mess up the diffraction pattern. Okay, so I think that's sort of all I have for my slides and stuff.
Well, I think that is a very good introduction, and hopefully all our students have had all their questions questions answered. If not, you could always email us and we can follow up. And let's all give Bill a virtual round of applause. And thank you so much. I think to wrap up, there's just a couple housekeeping things I wanted to get over with. We are winding down our signups for journal clubs. Actually, there's one more announcement I wanted to make. So in the course, I slotted in the syllabus that we will have a tomography section in April. Bill is doing double duty in the sense that he's also a lecturer in our tomography short course. We now have dates for that. The dates for the tomography short course will be April 12th to 14th. By being signed up for this, we'll forward your registration to the short course. We might actually ask you to re-register only so we have an appropriate email list, but details will follow probably in the next couple of weeks. This hasn't formally been announced, but they will be announced soon. So if you're wondering why we left out tomography from our syllabus, it's because we're having a separate section for this. Something that Micah has been hard at work at is our journal club. So to accommodate everyone, we have 5 different journal clubs. The assignments are here. Everyone online is also welcome to attend. They'll start next week on Wednesdays. I believe the class for Wednesday will be on image formation round 2. I think Micah is trying to put together image formation practical. So we will resume our journal clubs starting February 10th. I think that's the rest of the housekeeping that I have. And thank you for coming here this afternoon, and everything that we do will be put online. And if you have any additional questions for Bill, or if you just want to say thank you to Bill, just send us those good wishes and we'll forward them. Have a good afternoon.
Thanks, Ed. Bye.
Thank you.
Thank you. Bye.
Thank you.